my privilege to chair the higher order effects session. And the first talk in this session is going to be given by Ugo on model checking higher order effectful programs.
Thank you. Can you hear me well? I hope so. So yes, this is a joint work with Alexis Ghyselen, who unfortunately cannot come to POPL this year. And it's about model checking. And model checking, as we know, is one of the most successful paradigms for the verification of programs and systems. And in model checking, what you have is a system M, which can be anything like a process, a program, or just a cryptic structure, if you like. And together with M, you also have a specification phi, which can be a formula in temporal or modal logic, or even an automaton itself. And once you have M and phi, you can ask yourself whether M is a structure satisfying the specification phi in a logical sense. And this is the model checking problem. And for various forms of systems and properties, this problem has different natures. And sometimes it's decidable, sometimes it's efficiently decidable, sometimes it's even undecidable. And one specific case of this scenario is the one of higher order model checking, in which M is an higher order program, which can be equivalently taken as a higher order recursion scheme or a lambda y calculus term. Simple types are there, ground types are finite, and you have uninterpreted first order function symbols. So programs produce trees. And then it's natural to take phi as a tree property expressed as an MSO formula or a modal mu calculus formula, or equivalently again an alternating parity tree automaton. And this is a quite difficult model checking problem, which has been shown to be decidable by Ong in 2006, and then reproved decidable in other ways, even, for example, via type checking. The complexity of the problem is relatively high. It's k time complete, where k is the order of the program, of the underlying program. But there are tools available which can be used to verify concrete programs. Okay, so, fine. So we are interested in going beyond the realm of pure higher order programs as far as the left-hand side is concerned, as far as the class of programs is concerned. So for example, from lambda y or higher order recursion schemes, you can go towards infinite ground types, but if you do so, you are immediately bound to be undecidable because your programming language is equivalent to PCF. You can go towards polymorphic or recursive types. You land into another undecidable problem, but in this case, at least you can find sound, but although incomplete algorithms, verification algorithms. We are interested here in extending the language of programs with effects. For example, we would be interested in verifying that this OCaml program, which is built around two references, R and Q, does not produce any exception. The two references are changed by way of a recursive function, an higher order recursive function in a synchronous way. When at each iteration, the content of the two references are checked by way of the input function G, which just checks whether the content of the two references is the same, and only if it's different, it raises an exception. So it's clear that this program it does not raise any exception. We would like to be able to verify it by way of higher order model checking. The thing is that the literature offers some results in this direction. For example, there is some work about higher order model checking presence of non-deterministic choice, and in this case, well, it's easy to prove that you remain decidable. Sorry. Also, in presence of global store, you can do something. Even the tools provide some features around this effect. In case of exceptions, again, you are decidable. But for example, if you consider probabilistic choice, you are undecidable. There is a paper by myself, Naoki Kobayashi, and Charles Grelois a couple of years ago about that. So there are some discrepancies on the one hand. On the other hand, we would very much like to have a general theory about what is going on here and about which effects gives rise to a decidable higher order model checking problem. So what we do is to consider a calculus in which a reasonably large class of effects can be expressed. So it's EPCF. We follow Simpson and Vonnegut in doing so. It's a fine-grained call-by-value calculus with simple types and algebraic operations. And the simple types are such that the ground types are finite. Otherwise, there's not so much hope to get a decidable problem, a decidable model checking problem. Algebraic operations are parametric, and both the parameter and the argument to the continuation are ground and finite. Not so surprisingly, you can prove that the MSO model checking problem for EPCF remains decidable. And this is an easy homework, by the way. You just apply the usual CPS transformation to EPCF. You get rid of call by value. You get rid of algebraic operation, turning them into uninterpreted function symbols. And then you can just apply the old algorithm from usual higher order model checking. The thing is that, is this what we really want? Of course, we can, for example, take our running example, turn it into an EPCF term, and we can verify it by taking a specification phi in MSO. The thing is that, again, is this what we really want? Is it that MSO allows us to verify what we want? Well, in the case of global states, this is the case, but in the general case, this is not always the case. Let's see why. So again, following Simpson and Vonnegut, we can consider an extension of MSO in which the properties we want to verify about effects can be expressed nicely. So this is done by taking a set O of sets of trees, each of them corresponding to similarly looking trees. And this is, of course, a way to capture the observation we want to do on the effect tree. And the effect tree, of course, is nothing more and nothing less than a tree of algebraic operations you build when evaluating your effectful program. And each of these elements, each alpha, is then a property we want to check about our programs, and it becomes a modality in MSO. And so MSO parametric on big O is then an extension of MSO in which you can check programs against each possible modality alpha in big O. And this way we can prove that the MSO parametric on O model checking problem for trees generated by EPCF is decidable for certain effects. For example, for global state, exceptions, non-determinism, IO, and combinations of them. And how did we prove that? We proved that by, for each of these effects, we consider the underlying set of modalities O. For example, in the case of global states, this consists of the modality alpha P, RO, Q, where P and Q are states. And this modality captures all trees which turn the state P into the state Q along the only let's say, reasonable computation branch in the effect tree. And the thing is that all these modalities can be captured in MSO proper. So we can go back to MSO proper and use the old algorithm. While, for example, if you consider probabilistic effects, the underlying set of specification is pretty different. It's different in nature. It is quantitative in nature, and it cannot be expressed by MSO proper. Particular alpha greater than P, the modality we need here checks whether the probability of observing star from unit in the underlying effect tree is greater than P, which is not something you can do in MSO. Okay, so this way we have, let's say, found a way to isolate those effects for which an easy decidability result can be done, and then, and of course, some other effects like probabilistic choice are left behind. This is not, of course, an undecidability proof itself, but it gives evidence that for some effects we cannot go back to MSO. Is this the end of the story? Actually, no. What we also did was to consider the case of handlers. Sometimes your effects are not pre-interpreted. They are not given an interpretation by way of an external observer, but the interpretation of effects is left to the programmer. And so, as we have seen many times, for example, yesterday, handlers are precisely a way to do so. So we considered an extension of EPCF with effect handlers, and this can be done in a reasonably standard way by just extending computations with the with-handle construct. And the first argument of the construct is an handler H, which specifies for each possible algebraic operation the actual handler Ci. And this handler Ci depends on both on the parameter X and on the continuation R. And of course, the continuation can be used in a completely arbitrary way. And perhaps surprisingly, we proved that the MSO model checking problem for trees generated this way is undecidable. And the problem is that, again, the continuation can be used in very nasty ways by the handler Ci. And in particular, this allows you to simulate natural numbers as from Plotkin's PCF by way of effect trees and handlers. So what is particularly challenging here is not really simulating natural numbers themselves, but simulate test for equality, tests and pattern matching on natural numbers. This takes a little bit of an effort to be done. And but the key again is the fact that handlers can use the continuation in an arbitrary way, even more than once. You can take a look at the paper to see how this allows you to simulate natural numbers. So, is this once again, the end of the story? Can we do something about programs with handlers? The answer is yes, we can do something, but we have to pay a price, and the price is that we have to consider a very restricted notion of an handler, what we call a generic effect handler. A generic effect handler is an handler in which the handler itself uses the continuation in a very specific way. Okay, so it doesn't mention the continuation itself inside the handler as a free variable, but instead the value of obtained by evaluating the handler is passed to the continuation. And if you do so, you get a decidable model checking problem back. And the thing is that by doing so, by considering generic effect handlers, you get a calculus in which effect trees are transformed in a very disciplined way. Handlers act homeomorphically on trees, and you cannot do the fancy and complex stuff that generic handlers allows you to do. So, summing up, the contributions of this work is to we hope to give a fresh look at the problem of model checking higher order programs with effects, and the take-home messages are, on the one hand, that what matters is not much how you generate trees, but rather how you observe them. How you specify properties of those trees. And the other message is that, effect handlers, can be quite dangerous because they can use the continuation in very nasty ways. And this way, you need to be you need to be very careful and use handlers maybe in very specific forms. We would like to take a look, for example, in the future about extensions of MSO for which decidability can continue to hold, but of course this is quite this is going to be quite difficult. We are of course thinking about a specific form of probabilistic choice. But we also would like, and this is looks more less challenging, to prove a preservation property about decidability for combinations of effects. And that's it. Thank you very much.
Thank you very much for this talk. We have plenty of time for questions.
Thank you very much.
Yep.
Great set of results. But have you considered local states, and particularly the effect of dynamically allocating fresh names?
Okay, not yet. This is, of course, a very good question. It would be natural to consider them, but we haven't. For the moment, just algebraic effects. And,
they're sort of slightly influencing.
Yeah. Yeah.
Following up on Andy's question, if you do consider the local state, you might consider the generalization of parameterized algebraic theories.
Yes.
Have you thought about that?
Yes.
Yeah.
Exactly.
Thanks for the talk. I think for standard higher order model checking, it's efficient in practice. Do you have an idea whether the construction will probably also be similar or something, so this will also hold?
In the paper, we stress a lot about the fact that we haven't, for the moment, considered any complexity issue. So in presence of effects, we don't really know whether the complexity results, the classic complexity result about higher order model checking, hold unchanged or not. We are quite optimistic about the fact that the complexity stays the same, but we haven't done the job yet.
Okay, thank you for the talk. It was very interesting. I actually looked at the proof of undecidability in your paper, and regarding this last slide, have you thought about restricting the kind of programs that you can write so that the model checking problem becomes decidable?
Are you talking about?
How to tame the dangerousness of effect handlers.
So I think that this is a bit what we have done. So we have restricted the class of programs in the sense of restricting the class of handlers very abruptly. We don't know about the middle ground between general handlers and this what we call generic effect handlers, which is again quite restrictive. Look, the result of the handler is just passed to the continuation, and so this is equivalent to really using the continuation in add position once linearly. In this case, the trees are transformed in a more or less homomorphic way, and things work. But we don't know about the middle ground.
Thank you. How about if you allow multi-shot continuation, but you do not allow the kind of structure where you in the proof where you are able to escape the scope of a handler and have a recursive function that
I see.
goes over.
Yeah, this is a good idea. Yes, we haven't thought about it. Probably. Maybe CP. We have to check whether a form of CPS transformation can be used there. Probably not.
Okay. Thank you.
Yeah.
I think we have an online question now. Is that right?
Yeah, so there's a question from Discord. This is not the first talk that considers generic effect handlers, continuation only in tail position. I wonder what is the difference in expressivity with just function calls, functions plus dynamic binding maybe?
I don't think we go significantly beyond that. No. We are pretty close to a setting in which handlers are not there, and you try to simulate them, with different means. No. I agree.
So for the handler case, I presume you don't have an undecidability result yet, or only the model, MSO model checking is undecided, MSO problem is undecidable?
I mean, our result is, in the case of handlers, is this one, so MSO model checking is undecidable.
But do you really need MSO, or can you do with
No, I see what you mean. No, yeah, it's even reachability is is undecidable, yes. Even plain.
Reachability itself is undecidable.
Yeah.
And in general, do you need MSO, or can you do with first order logic with path quantification?
What do you mean you need for undecidability?
So for modeling all the problems that you have, do you need really
No.
signal logic?
I think that, typically, for example, in the running example, I couldn't show it, but with the running example, we need to prove the property I mentioned. You use a very simple alternating parity tree automaton, which doesn't even use parity. So, no, the kind of properties you need. I mean, MSO is huge. So.
Okay, great. I think we're out of time. Although I'm going to ask you one very last question. Yes. So your, what did you call them? Generic handlers. They seem to be the same thing as runners.
I could see. Yeah, I think so.
They are. Okay.
I mean, we with Alexis, we struggled a bit about terminology. We decided at the end to use this terminology, but I'm sure there is something.
So Andre Bauer and Daniel Arman have a paper on runners.
We should.
Okay, thank you very much.